Okay, so we have some loose ends to tie up for chapter 24. First, we haven't really talked much about potential energy, and potential energy is obviously a very, very important concept. So one of the things that we did see was that the potential energy formula looks like this. Well, I don't use the 1 over 4 pi epsilon naught. I usually use the K, but it's KQ1 Q2 over R. So one of the things that makes this different from potential is you'll notice it has the extra Q in it, right? So in other words, you cannot have potential energy with only one charge. You can have potential coming from a charge, but you can't have potential energy without having two charges. So it takes two to develop energy, right? Okay, so this is different from like kinetic energy, because kinetic energy is a property of one object, but kinetic energy and potential energy are different in that in order to have potential energy, you really need a system of objects. You need a spring in a block, or you need two masses attracting, or two charges repelling, or something. But you do have to have a Q1 and a Q2. Okay? So just let me write the V formula right under it. This is for 2-point charges. So we call that a 2-point charge system. And then we have the potential, which is KQ1 over R plus KQ2 over R. Okay? So this is for a two-point charge system. Point charge is a hyphenated word. So the first equation is saying that the potential energy is stored in the system. It's a property of Q1, Q2, right? It's like a linked kind of quantity. The second one is saying that the total potential near 2-point charges is the sum of the two individual potentials. Totally different formula. And this second one implies that the first charge has its own potential, the second charge has its own potential, but the first equation implies that, well, potential energy is a property of both. So that's kind of neat to see those two side by side. Okay, so what is the relationship between these? Obviously, there's a multiple of Q that needs to be introduced in order to create potential energy. So I've already given you some equations for this chapter, and you already know the laws of conservation of energy. But let's say you have a change in potential energy, or U final minus U initial, right? That could be treated as V final minus V initial. And this would be, I'm using Q2. I think our book uses Q1. In fact, I'm not going to use any subscript. I'm not going to use a numerical subscript. I'm just going to write Q test. So the V's have their own Q in them, but those are, of course, from the source charge. The test charge is the one that's experiencing the change in voltage. And then you would define the potential energy as the test charge's charge amount times the change in potential or voltage, right? Okay, so you could also switch it around and say that the test charge is producing a voltage which influences the source charges. You could actually do that. But either way, it's the same amount of energy stored in the system. Okay? All right, so that's probably all we need to say about it, is that there's that extra factor of Q there that converts delta V to delta U. And it's the feeler that gets multiplied in. All right, and then from there you can just use your conservation laws that you learned in mechanics. The second thing I want to bring up was, I said this already, the potentials in and on a conductor. So let's say that you have a conductor, right, of any shape. We've already said earlier in the year that if you were to charge this up with an imbalanced charge, let's say negative imbalanced charge, so you add some electrons, maybe you have like a glass gives kind of thing, or fur gives, and you end up with all these extra negatives. Lots of things happen, actually. They race to the outside. We talked about that. That's because they're trying to get away from each other. And therefore, it sets up a field, a vector field, perpendicular to the surface at all points, right? Like this. You guys remember talking about that? And the E inside is completely zero. Okay, completely zero. All right, so how does this play into like how V works? You know what I mean? Well, do you guys remember the relationship between E and V? How do you get one end to the other? So I'm going to let you answer that. I'm going to pause my recording and let you answer that. Okay, so the relationship between E and V is, if you want to find the E, you have to find the opposite of the gradient of V. And this produces basically derivatives in every possible dimension and a unit vector in every possible dimension. So if you're using x, y, z, you put in an I hat, j hat, k hat, and you also have a ddx, a ddy, and a ddz. Okay, so that's the relationship. Or you can also write this as an integral version, right? So think with me here. If this here is 0, and that's the derivative of something, what does that imply? So inside the conductor, there is no E field. That means the derivative is 0. Why would a derivative ever equal 0? So the implication is that if we're going to derive something and get 0, that something is a constant. So I was asking, what is the implications? Well, we're saying that V is not necessarily 0 inside. It could be, but V is definitely some constant. V is constant all throughout the inside. Okay, so that implies something about potential energy, because then if you take that concept and you stick a point charge inside, so a tester charge like this guy, Q test, remember the potential energy, or let's not necessarily do potential energy, let's look at it as from a work perspective. From a work perspective, work is Q test charge times delta V, right? So if you were to move this guy around in here, just kind of translate him around, looks like field lines. I didn't mean to make him look like field lines. If you move him from one spot to another, he experiences no change in V. So that would be 0. And the work done to accomplish this is 0. In other words, it requires no work at all to move that thing around on the inside. Okay, so you can move it anywhere you want inside there. It would require no work at all because there's no forces. There's no forces acting. Okay, or another way of saying it is if it's already moving, let's say it already has an initial velocity, it might move throughout the interior, but it would not experience any changes in potential energy, which means it would continue with all of its kinetic energy. It would not need to trade any kinetic energy to potential. There is no potential stored ever. Okay, so that's an interesting concept. And what happens, this is something that we've tried to avoid in the past, but what would happen if you took your test charge here and you displaced it from inside right onto the surface? What would happen then? Okay, so this is not so obvious maybe. So the question was, what happens if you do a small displacement ds from inside to directly on the surface? And the answer to that is the surface is an equipotential, which means nowhere on this surface do you experience a change in V. You could be at any point on this surface and you would experience the same potential. Why? It's a conductor, right? Imagine trying to measure the difference in voltage using a probe. If you put one probe here from your voltmeter and one probe here, you wouldn't expect a different voltage. Why would there be a different voltage, right? Okay, so there's no difference in voltage, and that makes it an equipotential by definition. Okay, so that being said, the voltage on the surface, the potential on the surface is the same constant we had on the inside. So remember when we said that V is constant on the inside? It's the same constant on the surface. So how much work then does it take to bring it from inside to directly on the surface? Again, 0. Okay? So we've avoided the surface from a field perspective, but we could say that we could put this charge, test charge on the surface, and it wouldn't experience any work done, or it wouldn't store potential energy. Okay, let's talk specifically about the sphere itself, because the sphere is always the interesting case, you know what I mean? So this is kind of a fun thing to do. Here's a sphere, and it's a conducting sphere, right? Conducting sphere. And because it's a conducting sphere, I don't care if it's full of metal or hollow. That doesn't matter to me at all, because if it's made of a conductive material, the electrons are on the outside anyway. You could go in here and you could choose any Gaussian surface. Pick your favorite shape. Cylinders, Gaussian spheres, whatever you want. Okay? And there is no flux. No flux means no field. No field means no change in potential, and therefore constant throughout. So nobody cares about the inside, actually. If you tried to plot the voltage starting at the center and going outwards, so let's call that distance r, you will eventually hit r equals r, right? You'll eventually reach the edge of the sphere. But the voltage function would be totally constant the whole time until you hit the surface. As soon as you hit the surface, now it looks, once you're out here, once your r exceeds r, the charged sphere looks like a point charge from that point on. So it's now going to be, on the inside, it's just V equals constant. On the outside, it's going to be V equals KQ over R. So this is not a point charge, but it appears like a point charge forever after R equals R. So it's going to drop off as 1 over R. So it's going to look like KQ over R here, and it's just going to look like V equals V naught here. Very interesting scenario, and definitely a piecewise function in the true sense of the math term. So much for the idea that there's no piecewise functions in nature, right? Most of them are differentiable curves, but not here. Okay, any questions on that? Now the question might come up also, is there an asymptote here, or is this actually a starting value? That's an excellent question. That's an excellent question. So we might have to not answer that question, because the question, it gets into the question of what's happening right on the surface. And we said a minute ago that this flat line, right? This flat line is going to go until we hit R equals R. As soon as we hit R equals R, that voltage on the surface is exactly the same as inside. So that's a closed point. But then after that, how close do you have to be before it's considered a finite potential? Is it infinite potential, or is it finite? I should have thought about this before recording, but I think it might be finite. The reason I suggest that is because we're measuring from the center of the sphere, so R is not 0. Yeah, R is not 0. Little r is not 0, so you're doing KQ over R, but R is already capital R. So I would actually say, I think we've answered that question. That point right there is the point KQ over capital R. And then after that, it's KQ over little r. Does that answer your question? Yeah, it's not an asymptote. Yeah. Good question. That was an investigative question that I thought of as soon as I mentioned it. But the asymptote is actually back at R equals 0 over here. And so it doesn't affect us at all. Good question. Okay, so that's kind of a fun graph. And you could probably write it as a piecewise function. So let's do that real quick. This is our calculus coming in now. So it's going to be a constant when R is between 0 and capital R. And then it's going to be KQ over capital R when R is exactly R. And then it's going to be KQ over little r when R is bigger than R. There's your piecewise function. So you might actually see this on the AP test. You might actually be given a piecewise function. And you guys definitely know how to do that stuff from calc class, right? It's not a big deal. And that that actually does conclude the chapter. So I don't think I will need time tomorrow. So maybe tomorrow we can do some Q&A.